In the last lecture, we defined different for a number field and then we defined different for local fields, and we started with this theorem that that relates the local different to global different. So, let me recall, we had just started proving it. So, let me do that from the beginning. Let me recall the statement of the theorem and we will see a proof today. So, let L over K be a number field then be an extension of number field of number fields, then the global different L over K is a product of local difference. Okay. And as I said, this is somewhat tricky. So, the way to write this would be as follows. So, you vary overall primes P inside OL dL P over Kp. Okay. So, small p is P intersected with OK. And one should be careful about what this statement means, because on the way we have defined difference, on the right hand side we have ideals inside Kp, but that is not what we exactly mean. So, how do we interpret, I said this last time, how do we interpret this formula? So, this formula means if dLp over Kp is p to the power Ep, or maybe E is a bad notation, let me say A sub p for Ap greater than or equal to 0. So, this is an ideal in O sub p. But what we mean is that dLk, this is product over all p to the power Ap for and these are ideals inside these are ideals in OL. Okay. So, that is what this formula means, and that is how one interprets it, and we started the proof as follows. So, we said that trace from L to K of eta is equal to summation over all p dividing some fixed p trace from Lp to Kp of eta for all eta in L. And for this I gave an exercise which said that any alpha in L can be written as alpha equals eta minus eta prime for eta prime in L, such that L is k eta and it is also k eta prime. So, any element of L can be written as a difference of two generators. So, that is what we used to prove this formula. So, we prove it first for generators and then we use additivity of trace and this exercise to prove it for any eta in L. Okay. So, now we want to prove we want to go back to the proof. So, here is the first claim. So, if alpha belongs to dLp over Kp inverse, then so this is alpha is in this and it is in the intersection of this and L, right. As I said, this is a local ideal a priori. So, I want to consider only global elements for the comparison to make sense, then it is also in this, right. This is what we want to show. Okay. All right. So, how do we yeah, maybe I'll rewrite this statement again. Let me rewrite this again. So, if alpha belongs to LP over KP inverse for all P dividing small p, and this is sort of in this intersection as I said before, then alpha belongs to L over K inverse. Okay. Now, what does that mean? So, alpha belong to LP over KP inverse intersected with L, if and only if alpha, so trace from LP to KP of alpha beta, maybe since I am writing if and only if, let me get rid of this L, is equal it is contained in OP for all beta inside O capital P. Okay, so that is what this means. Now, we take alpha such that alpha is integral at all primes different, so all primes other than let me not use the word different, other than those dividing P. What does this mean in mathematical symbols? This means alpha belongs to OQ intersected L for all Q not dividing P. Okay. So, then trace of LP L, let me use capital Q here. So, LQ over KQ of alpha times beta is also in OQ. Okay, here Q is Q intersected with OK, right. So, this means that so therefore, trace from LQ, and this is for all beta in O capital Q, right. So, this means that trace oops, this is fine, I want to erase this to correct it. L to K of alpha beta belongs to OK for all beta in OL. Right. Hence, alpha belongs to DL over K inverse. Right. So, thus we have proved the claim. That product over P dividing P DL P over KP inverse is contained in DL over K inverse, right. And this is same as saying that this is same as saying equivalently product over all capital P dividing small p DL P over KP divides DL over K. So, we have proved one divisibility. Now, already this is very nice because DL over K is a non-zero ideal in OL, right. Hence, it has only finitely many prime ideal factors. right. This already shows, therefore, dLp over Kp is equal to OP for all but finitely many P's. Right. Hence, this product over all P dLp over Kp is a finite product, right. A priori, this in the statement of the theorem, and maybe I should have pointed it out when I stated the theorem, it looks like this is an infinite product, right. It looks like this is an infinite product, but it is not an infinite product. Okay. It is a finite product. Yeah, it is a finite product now that we have proven the first claim. Okay, so that is a good start. Now, the next claim would be to show that, oops, the next claim is to show that dl over k divides product over p dLp over Kp, right. That would be the other direction. So, again we do this prime by prime. Okay. So, let us say p to the r is the largest power of p dividing the global different. Then we want to show that that dLp LP over Kp is also equal to p to the r, right. It is p to the r, right, or at least maybe this would be what we eventually get, but we want to show that p to the r divides this, right. So, we want to show this. Now, what does p to the r dividing this means, i.e., we want to show that del Lp over Kp is contained in p to the r, okay, which is same as saying that p to the minus r is contained inside del Lp over Kp inverse, right. We always work with inverse different because that is what has explicit description. Okay. So, what I do is I take beta which is in p to the minus r, but not in p to the 1 minus r. Okay. So, when I just add 1 to, when I multiply this by p, I get a slightly smaller ideal, and I do not want it to be in that ideal. Okay. So, if I take so for any alpha in OL, what I have is trace from Lp to Kp of alpha beta. This is inside O small p, right, by definition of what so this is what I want. Okay. So, we want to show this, right. Now, how do I show this? Well, we use this formula. So, use trace from L to K of alpha beta is equal to summation p dividing p trace. So, maybe this is a bad notation because we have fixed a p. So, maybe p primes p prime, okay, it is not a P prime dividing P, trace from LP prime to Kp, right. We are taking all primes above the small p here. Okay. Now, beta belongs to O P prime for all P prime not equal to P. P's are fixed prime above small p, right. Hence, trace from LP prime to Kp of alpha beta, this belongs to OP prime, O small p for all p prime not equal to p. Okay. On the other hand, as p to the r divides this different, the trace from this to this is also contained in OK. Okay. Similarly, trace from LQ to KQ of alpha beta, this is also contained in O small q. So, we have this element that is integral everywhere except possibly at p, but that cannot happen. Okay. So, using star gives, we do not really use this, but I just wanted to say that that also holds. Using star gives trace from LP to Kp of alpha beta is in OK, right. And so, that is, yeah. So, hence P to the r divides dl P over Kp. Okay. All right. So, that finishes proof of the theorem that we want. So, now we have done something very nice, very useful. We have shown that the global different is product of local different. This still does not tell you how to compute difference, but at least one would think that computing local different would be easier than computing global different, and that is indeed the case. And in this lecture and the next one, this is what we will show. Okay. And as a preparation for that, let me prove the following lemma. It's something about local situation. We will show that the ring of integers in an extension of a local field, in a finite extension of a local field, is generated by one element. Okay. So, this need not be true for rings of integers of number fields, but at least in the local case this is true. So, let me state the lemma. So, let L over K be finite extension of number fields, let P be in OK and P be in OL above P be non-zero prime ideals in respective number fields. Then there exists alpha in L such that well, first of all, L P is K sub P alpha, but moreover O sub P is also equal to O sub small p of alpha, right. So, it is this second thing that we are most interested in. The first one, of course, it just comes from primitive element theorem. So, that is not such an interesting situation, right. Okay, and I do not think we use primitive element theorem here. We will directly prove the second part, that O sub capital P is O sub small p alpha, and that will of course give us the statement about fields also. Okay. And the reason why this holds for local things but not global things is, again we will use some limiting process, and those limit only exist in O sub capital, I mean the local situation, right, O sub capital P or O sub small p. So, this is an important technique that you should understand well, because it is useful in many places. So, what you do is you look at K sub p, this is O L mod p is finite field, it is a finite extension of K sub small p, which is OK mod p, right. So, there exists z, let us say xi in K p such that K p is K small p of xi. So, so there is a map from OL to K capital P which is surjective. So, let alpha be in OL such that alpha bar in Kp equals xi. So, we can always do that. Right. Okay. So, if we consider the ring O small p of alpha inside O p, then of course every element of K p is represented by image of an element in O small p alpha, right, which means, so I like to draw diagrams in algebra. So, I have this surjective map, right, and this thing contains O sub p alpha, and there is a map like this which is simply composition of the two maps, right. You take injection and then you take this vertical injection and then you take the surjective map, but this is also surjective, right. This is what this is saying. Okay. You do not need to go to the big set to get something is surjective, it is enough to go to the to O sub p alpha. Of course, that does not prove that O sub p alpha is equal to O sub capital P, and in fact that need not even be true, right. So, what do we do? Well, we know this fact, we know that p to the m modulo p to the m plus 1 is isomorphic to O p mod p for all m bigger than or equal to 1, let us say, right. And what is the isomorphism? The isomorphism is easily given in this direction, x goes to x into pi to the m, where pi to the m, where pi belongs to p but not to p squared, right. So, we want to find, if O sub p alpha contains an element in p minus p square, and as I said, it need not be true that O alpha contains an element like this. We may need to change our alpha, okay, and that is what we are going to do. Okay, so what I am going to do is the following. So, let phi bar of x in K sub small p of x be the minimal polynomial of xi over k sub small p. Right? The xi is algebraic over k sub small p. So, it will have a minimal polynomial like that. Let phi of x in O small p of x be a lift of phi bar of x. Right. So, we can always take a lift like that. Sorry, let me take that lift not in O sub p, but actually in O sub k. Okay. Right. Now, let phi bar of x be the derivative. I mean, derivative for polynomial is just a formal process, right. Phi bar of phi prime x bar, this is in k p of x, is not identically 0. Right, because phi of x is a separable polynomial, right, as k p, or maybe even let me just say xi is yeah, maybe it is more accurate to just say k p is k p over k sub small p is a separable extension. Okay, right. Therefore, by the same fact, phi prime bar of xi is not equal to 0, right. The minimal polynomial does not have multiple roots, and degree of phi prime bar is less than degree of phi bar. Okay. So, let pi be an element in p minus p squared. Okay. So, we have two facts. We have that p divides phi of alpha as phi of alpha mod p is equal to phi bar alpha, which is again everything is mod p. I mean, I do not need to write mod p here because it is bar already. So, so this is phi bar of alpha bar, which is phi bar of xi, which is 0, right. So, that is this fact. And then if I look at phi of alpha plus pi, this is congruent to phi of alpha plus pi phi prime of alpha modulo p squared. So, this is like Taylor series expansion, right, where we just consider first two terms because other terms will be divisible by pi squared, and so modulo p square they are not relevant. Again, this is just for polynomials, so it is very easy to verify this. You do not need analysis to, I mean, Taylor expansion is just an intuition. You can prove this extremely easily for polynomials. So, maybe take this as an exercise. Okay. All right. So, what do I know now? Right. Okay. So, I know that this is in P. I know that this thing is in P. Right. But not in P squared. Okay. And yeah, because of this I know this is in P. So, if both these are in P squared, then we get a contradiction. So, if both phi of alpha plus pi and phi of alpha are in P squared, then pi of phi prime of alpha is also in P square. This is a contradiction. Hence, at least one of phi of alpha or phi of alpha plus pi is in P minus P square. That is what we wanted. So, that is hence OP of alpha is equal to OP, or OP of alpha plus pi is equal to O capital P, right. Remember, so alpha plus pi bar is equal to alpha bar is equal to xi, right. All right. So, that is all we wanted to prove. Okay. So, this is a very useful lemma, because it tells you that although you cannot generate rings of integers in global field by one element, you can generate rings of integers of a local field by one element. So, this primitive element property, it always holds for local rings in the rings of integers in the in local fields, but not necessarily in global field. And because we have related global different to local difference, if you want to calculate difference, or if you want to calculate for many calculations, it is enough to use this in case of local results, and that local rings, and that is what we are going to do next time. We will see exactly, well, maybe not exactly, but we will see how to calculate the different in most cases. Okay. So, that will be the content of next lecture. Thank you.